Hi, 4th grade, it's Mrs. Boswell again on day 3 with wave patterns and information transfer. I hope you had fun with your science experiment yesterday. We're going to do a little bit of reading today about our wave patterns and amplitude and kind of covering over some of that vocabulary for our science experiment that you will do on day 4. So let's get started. It says, I can model and explain how waves move. It says, today we're going to be reading to understand the words wavelength and amplitude. This will help us with our investigation on day 4. Oh, look, I keep finding the typos as I do this. Fun stuff. So, as we do this and as you read today, I would like you to take notes in your science spiral notebooks. So you're going to need your science book and then your science spiral notebook. Now, remember you can pause the video at any time to stop and take notes or to listen to something again. You can rewind it. So here we go. Our first piece is sound and light. Sound energy. If you drop a book onto the floor, you hear a sound. Some of the following books' energy of motion has changed to sound. Sound is a type of energy. Sound is produced by moving particles of matter, so it is a type of kinetic energy. Remember, we've learned about this before. Producing sound. Vibrations. If you pluck a guitar string, it moves back and forth quickly. This back and forth motion is called a vibration. This vibration produces sound. You can feel a bright vibration if you place your fingers against your throat while you talk or hum. The vocal cords in your throat vibrate when air moves past them. These vibrations allow you to speak. All sounds begin with a vibration. The drum shown here is surrounded by air. The vibrating parts of the drum bump into the air particles. These particles bump into other air particles. The drum's vibration squeezes air particles and then they alternately spread out. So here you have that picture, and every time that drum is hit, it's vibrating, and it's vibrating those air particles. The air particles spreading out produces regions of air that have many particles called compressions, and regions of air that have fewer particles called refractions. The compressions and refractions move through the air as a wave carrying sound energy. So here you kind of go, here's your compression, and then these are your refractions. So as a sound wave moves through air, the density of the air changes. The air does not move along with the wave. So here we go, sound waves. A series of refractions and compressions traveling through a substance is called a sound wave. The substance through which the wave traveled is called the medium for the wave. So it's that substance through which the wave travels is called the medium. So whatever it's flowing through. So in this one, it was flowing through air. Examples of mediums include metals, water, and air. Like all waves, sound waves carry energy. When they pass through a medium, the medium is not permanently moved. Energy, however, is moved through the medium. So that's a lot of information to take there. So they're really talking about the medium is metal, water, or air, and that's where waves can move through. So if I had some type of metal, it might be moving through that metal. If I had water, there are waves that move through that water, sound waves. Okay, because you would have your animals that would have to have sound. And the biggest one, or the one that really makes me think about it, is dolphins. When they make their sounds, those sound waves have to travel through water so that other dolphins can hear them. So that's an example. So here we go. Direction of sound waves. Sound waves vibrate the medium in the same direction that the energy moves. They are called longitudinal waves. Think about how a coil toy or a spring moves when you push it together and pull it apart. Sound waves move in the same way. I wonder if you're enjoying my dog snoring in the background. Sophie. She wants to be a part of our lesson today. All right. We can also show sound waves as a series of peaks and dips. The peaks represent the high density of air and compression. The dips represent the low density of air in refractions. So I would have high, low. Or over here, high, lows, high, low. Okay. However, remember, the air does not move up and down like the peaks and dips. So the air is not really moving, the sound wave is moving. When sound waves hit an object, the object starts vibrating. The object is moved by the energy of the wave. The movement is how sound from a loud airplane or stereo can rattle windows. You can feel the vibrations caused by such loud sounds. All right, sound energy, how sound moves. Speed of sound and state of matter. Ooh, remember that was that question that those four students put in there, and they were talking about the matter and how sound travels. So here we go. Sound can travel through solids, liquids, and gases. In fact, sounds tend to travel with the greatest speeds in solids and the slowest speeds in gases. For example, sound travels through steel at almost 6,000 meters per second. But sound travels through air at only 343 meters per second. Differences in the speed of sound result from how far apart the particles are in the medium. So if my medium is air, those particles are further apart. Okay? The particles carry sound energy, and their collisions are how sound energy travels. And in a solid, the particles are close together, so they quickly collide. In gases, particles are far apart. Collisions are less frequent, so sound travels more slowly. So speed of sound and temperature. The temperature of the medium also affects the speed of sound. In warmer air, particles move faster. As a result, they collide more often and transmit sound faster. Sound in space. Ooh. Sound cannot travel in any area without particles of matter. For example, outer space has few particles, so there is no medium for sound to travel through. Outer space is a vacuum, a region that contains few or no particles. So, how are they hearing each other? They're usually speaking on a walkie or some type of communication tool they use. It says, did you know sounds cannot travel through space? 2 astronauts on a spacewalk can talk using radios and can hear one another only because their air is inside of their helmets. It says from the far side of a ballpark, you can see the ball being hit before you hear the crack of the bat against the ball. Because remember, it takes longer for sound to travel through the gases or the air. All right, absorption of sound. When a sound wave hits a wall, some of the energy of the wave is absorbed. Absorption is a transfer of energy when a wave disappears into a surface. The energy itself does not disappear. Absorbed sound energy transforms to the thermal energy, heating the surface that it absorbs it. Reflection of sound. When sound waves hit a flat, firm surface, much of their energy bounces back. An echo is a specific reflected sound. You can hear an echo if you make a loud noise in an empty room. Echolocation. Echoes can be useful. Bats make sounds that echo off their prey. The returning echo tells the bat where their prey is located. This skill is known as echolocation. Whales and dolphins also use echolocation to learn about their surroundings and to find food. And remember, we just talked about dolphins earlier. Sonar. Scientists have developed systems called sonar that works the way echolocation does for animals. Sonar stands for sound, navigation, and ranging. It is used underwater to find objects. The sonar system sends out sound waves that reflect off objects. The return time and direction of the sonar echoes are used to calculate the location of the object. So here is a squid, and that boat is sending off the sonar sound, right? And it's going down. It's going to bounce off of the squid and come back. So boats use sonar to find objects underwater. A lot of boats will use it to find, is there land underneath them or what is underneath the boat? It says sonar technician, interested in finding out what is beneath deep ocean waters. Sonar technicians use sonar equipment to locate all sorts of objects in the water. Sonar or broad ships can be used to find marine life, other vehicles, or even sunken treasures. Learn more about becoming a sonar technician in the career section. Oh, my silly dog. All right, sound energy, pitch. All sounds are made by vibrations, but you hear them differently because of differences in their properties. Like all waves, each sound wave has a wavelength and a frequency. In sound waves, wavelength is a distance from one refraction to the next. If you represent a sound wave as a repeating pattern of peaks and dips, wavelength is the distance from one peak to the next peak. Frequency is the number of vibrations a source of sound makes each second. The more vibrations there are, the higher the frequency of the sound. When you strike a bell, it vibrates quickly. The vibrations produce sound waves with a high frequency. Now you can hear him. When a drummer hits a bass drum, it vibrates slowly. The vibrations produce sound waves with a low frequency. Pitch is how we hear the frequency of a sound wave. If a sound wave has a high frequency, we hear the sound as having a high pitch. If a sound wave has a low frequency, we hear the sound as having a low pitch. So high frequency sound waves have peaks close together and short wavelengths. So here this dog is yapping arf, 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 real fast. Low frequency, ooh, like my beagles that are in the room with me, they have a low frequency sound. They have a really deep bark, so they're further apart. All right, changing pitch. Changing the pitch of musical instruments. To make a sound higher in pitch, increase the number of times it vibrates each second. On a string instrument, shortening the string increases the pitch. On a wind instrument, shortening the tube increases pitch. A shorter tube produces a higher pitch because the air inside vibrates faster. So remember, when those particles are closer together, they will vibrate faster, or you'll hear it faster. Okay? So a Doppler effect. As you move towards the source of a sound, the pitch sounds higher. As you move away from the source of a sound, the pitch sounds lower. Recall that frequency is the number of peaks of a wave that passes by a location each second. If you move toward the source of a wave, the peaks move past your ear faster than if you were standing still. If you move away from the source of the wave, the peaks arrive at your ear more slowly and the pitch is lower. A change in frequency produced by moving toward or away from a sound wave is called the Doppler effect. Any movement can cause a Doppler effect, but only fast speeds will change a pitch enough for you to notice it. So the sound of an ambulance siren changes as the ambulance gets near or farther from you because of the Doppler effect. Okay. All right, so this is what's really going to come in, is this word amplitude and our volume is what's really going to help you with your science experiment tomorrow. And wavelength. So, sound energy, volume. The height of a sound wave is its amplitude. The amplitude describes how dense the air is in the compression or refractions compared with normal air. Amplitude is a measure of the amount of energy a sound wave has. So, the other day when you were plucking the cup and you would pluck it softly, the sound wave was lighter. As you plucked it, gave it more strength, it was harder. It says amplitude affects the volume or how loud a sound is perceived. Scientists measure the volume of sounds with units called decibels. The table lists decibels levels for various sounds at certain distances. A jet taking off is 130 decibels. A chainsaw, 110. A garbage truck, 100 decibels. Levels at which hearing damage can begin is 85. Average city traffic that you might hear is 80 decibels. Normal conversation is about 60. Whispering is about 30 decibels. A human breathing is just 10. So if you just breathe, that's only 10 decibels. I bet Sophie's snoring over here behind me is about 30 decibels. All right, so we have wavelength and amplitude. Okay, so long wavelength, low amplitude. Okay, so if I have a wave and they are closer together, or long waves, I have low amplitude. Okay, if I have long wavelengths I can have high amplitude. Short waves, low amplitude. Short wavelength, high amplitude. So, energy, changing the volume. You can make sounds louder by using more energy. If you hit a drum harder, for example, you give the drum more energy. The extra energy increases the density of particles in the compression of the sound waves. Increasing its volume, the refractions will be less dense than before. Medium. A sound wave has a smaller amplitude when it travels through a dense material. The wave has the same amount of energy. Even though the amplitude is smaller, there are more particles moving in the medium. So remember, like in water, it's going to move faster because those particles are closer together. Distance. Volume is lower farther from the source of sound. The energy of the sound wave spreads out as it travels. Less energy at any one point means a lower volume. Hearing sound. So here's your hearing system. Remember, this is what helps you hear. We hear when sound waves travel into our ears. The diagram shows how the sound waves move from the ear to the brain. What happens when a sound wave reaches your ear? So here I have a sound wave coming in. So this is my outer ear. The outer ear collects the sound waves like a funnel. It directs the waves into the ear, and then it goes here to your eardrum. The sound waves make the eardrum vibrate like the head of a drum. Okay? Then we move here to the middle ear. The vibrations are picked up by 3 tiny bones in the middle ear. The bones are the hammer, anvil, and the stirrup. Okay? Here you have the inner ear. This section right here is the inner ear. The stirrup passes the vibrations to a coiled tube in the inner ear. This tube is filled with fluid and lined with tiny hair cells. And then here we have our nerve to the brain. The moving hair cells signals a nerve in the ear. The nerve carries these signals to the brain. The brain interprets the signal as sound. Isn't that crazy how our ears and those tiny hairs and nerves can carry that to your brain? Very interesting. All right, so here's what I want you to do. I want you to please define these words, wavelength and amplitude, and then also give 2 examples. Give me examples of wavelengths and examples of amplitude. And that will be your end of your science lesson. Great job today.